Hello class and welcome to lesson 24. In this lesson, we will differentiate between ground and excited state electron configurations. We will relate the change in Bohr structure for an atom as compared to an ion. And we will compare the number of electrons in atoms and ions and how that change in the number of electrons impacts the radius of the species. Make sure you're using guided notes as you follow along. Write down any questions you have and be sure to ask them in class. Let's go. Recall that Niels Bohr did an experiment called a flame test, and he observed that various elements give off different colors when placed in a flame. This went and had him determine that the energy of electrons is quantized, or a specific quantity related to their position on a principal energy level, also called an electron shell or an electron ring. Here is a diagram showing the Bohr models for the first 20 elements on our periodic table. Make sure you take special note of these three important patterns that we see in the Bohr model. Chemical families or groups, which are vertical columns here, have the same number of valence electrons. Elements in the same period or row have the same number of principal energy levels, which we will abbreviate capital PEL. Principal energy levels, again, are the number of electron rings. All the elements in the second row happen to have 2 electron rings, while all the elements in the third row have 3 electron rings. On the periodic table, the row number corresponds with the number of electron rings. And finally, the further from the nucleus an electron is, the more energy it has. In the diagram above, you can see yet another review of how the subatomic particles can be shown in the periodic table and the isotope symbol. Recall that the mass number, which is always a whole number, is in the upper left-hand corner. Mass is due to protons plus neutrons. Electrons have no mass and are not considered in this equation. Protons determine the identity of the species and the nuclear charge. The electron configuration provided on your periodic table is the electron configuration for the neutral atom. When the species is not an atom, it will have a charge, making it an ion. The charge is determined by subtracting electrons from protons. When looking at an electron configuration, it is important to realize that the outermost principal energy level, the one with the most electrons written to the right, will be the valence electrons. Valence electrons are important to chemistry, or they are exactly what defines chemistry. When elements form bonds to make compounds, they gain, lose, or share valence electrons. Carbon has 4 valence electrons. Chemistry is the study of making and breaking chemical bonds. All chemical bonds are formed by valence electrons. Valence electrons make bonds by gaining, losing, or sharing electrons so that they can obtain the same electron configuration as a noble gas. This is called the Octet rule because 8 valence electrons is the number of desired valence for most noble gases. Like every rule in chemistry, of course there's one exception. The noble gas helium only wants a valence of 2 because it only has 1 occupied principal energy level. Let's put this all together by examining these 2 isotope symbols. In the first symbol, we know there are 17 protons because the bottom number, the atomic number, is 17. To find the neutrons, we will subtract 37 and 17 to get 20. So there are 20 neutrons in this first example. The number of electrons is found by using the charge equals the protons minus the electrons. In chemistry, we do not typically write ones, so this negative charge means it's a -1 charge. -1 equals 17 minus what number? That means there must be 18 electrons. Now looking at the element box above, you can see that chlorine atoms have an electron configuration of 287, but 287 only has 17 electrons. This is an anion, a negative ion. It has 18 electrons. We always add or remove electrons from the valence shell, so its electron configuration will change to 288, and the rightmost number is its new valence number. So this chlorine 37 ion has a valence of 8. Examining the symbol on the right, you can see that it is an atom with no charge. Every chlorine atom has 17 protons. To determine the number of neutrons, we subtract the protons from the mass number. There are 18 neutrons in chlorine 35. Since this is an atom, the number of electrons is equal to the number of protons because the charge is 0. To find the number of electrons, you can simply add up the electron configuration. 2 plus 8 plus 7 is 17. Since this is an atom, as indicated by no charge in the upper right-hand corner, you can simply copy the electron configuration from the periodic table. This atom of chlorine 35 has an electron configuration of 287, and the rightmost, or furthest from the nucleus, number of electrons is 7, so the valence number is 7. Recall that Bohr's experiment involved the movement of electrons. When electrons absorb energy, they are able to move to a principal energy level or an electron ring further from the nucleus. When this happens, the electron is said to be in the excited state. But nothing is really observed at this time. When the electron returns to the more stable, lower energy, original electron configuration called the ground state, the energy absorbed to jump away from the nucleus will be transformed into light energy as it returns back to its original position, the ground state. It is very important that you're able to describe the absorption of energy, the movement from ground to excited, and the return to the ground state with the release of energy, and this is the form of. There is one very important rule you must follow when writing electron configurations from elements in the ground state, and that is that each principal energy level cannot exceed the maximums we discussed earlier. The maximum number of electrons in the first principal energy level is 2, the second is 8, the third is 18, and the fourth is 32. Let's do this example together. Here we were asked to write the ground state and excited states of various elements. To write the ground state electron configuration, you simply use your periodic table. If you cannot find the symbol on your periodic table, go to reference table S. Find the symbol and its corresponding atomic number, then go back to your periodic table. Find the element and write down the electron configuration as given. The electron configuration given on the periodic table is always the lowest possible energy state called the ground state. To write the electron configuration of a species in the excited state, take an electron from a lower energy level and move it to the right. So in the example for sodium, you can move an electron from the second principal energy level to the third principal energy level, or you can move an electron from the first principal energy level to the third principal energy level, but you always must make sure you do not exceed the maximum. Notice that the electron configuration 192 is not acceptable because the second level can never exceed 8. One trick you can always use here if you can't remember the maximums is just add another energy level. So for sodium, we can take its last number, the number 1, and move it from the third shell to the fourth shell. So its excited state could be 2801. Notice that in the ground state and the excited state, the electrons added together always equal the atomic number of the atom. Barium is element number 56. When we make its excited state, notice how we took the valence of 2, removed 1 electron from that shell, and moved it to the next principal energy level. This is always an acceptable way to write the excited state electron configuration. There are many possible correct answers when writing excited state electron configuration. You just need to make sure that you never exceed the maximum number of electrons in the first 4 principal energy levels. There are more principal energy levels, but you do not need to know the maximums after the 4th principal energy level. Let's look at this example looking at atoms of lithium and sodium. Both lithium and sodium have a valence of 1, but sodium's valence electron has more energy because it is in the 3rd electron ring or principal energy level, while lithium's is only in the 2nd. The further from the nucleus, the more energy an electron possesses. For both of these atoms, if we add energy, we can make electrons jump up to higher energy levels. When the electron returns to the ground state, as it falls back down, it will release the energy in the form of light, creating a bright line spectrum. This concludes lesson number 24. If you have any questions, write them down and make sure to ask them in class. Can't wait to see you!